to the lecture series in cell culture technology. So, we are in the 5th week and today we are initiating the 4th class of the 5th week. So, if you remember, in the last class we talked about a case study where a company who has a set of molecules or drug molecules which it wishes to test for Alzheimer's patients. So, in order to do that, the first level of test will be on the cell culture plates, whether it is working or not. So, we reached up to the point how to set up a cell culture or neural cell culture of hippocampal neuron, since these are the neurons which dies during Alzheimer's disease. So, there is a neurodegenerative, it is basically Alzheimer's is a neurodegenerative disorder which leads to the death of hippocampal neuron over a period of time, and eventually the individual loses his or her own identity, and eventually they die, and it is a kind of a very sad disease, because you are you because you know your name, or you could identify yourself in a surrounding, but in an Alzheimer's patient you do not know who you are, because all your memory traces fades because of the death of the hippocampal neurons. And there are a lot of efforts across the world to understand what these kind of disease is, and since it picks up at a later age, so you need lot of care, and it's especially for such patient it is very difficult to hold them at home, because if you are going out for work and you have an elderly person who is suffering from Alzheimer's, there are a lot of issues, because they may get lost, they may go out of the house and they may get lost because they won't be able to identify their own house. It's a kind of a very sad and a very sorry state of affair. So, with this background, we were kind of developing a case study that what a company can do in terms of to screen the drugs. So, we went to this far. So, this is where we were. Just before I start, so today we are initiating our week 5 and our lecture 4, okay, W5 L4, fine. So, now say for example, to keep it simple, you have 3 different drug molecules X, Y and Z, right. Now, these 3 molecules the company believes could influence or could help in the Alzheimer's patient. So, in order to test that, you have to have certain parameters. What are the parameters? See, for example, again this is whole hypothetical situation. So, we will be going by, we set the parameter, we say X, Y, Z, these are the drug molecules, fine. Drug molecules against Alzheimer's. So, what are the testing parameters or evaluation parameter, testing or evaluation parameter? Here are the evaluation parameters. So, it is believed that all these 3 drugs increases the number of synapses in a network. This is all hypothetical we are talking about, okay. Number of synapses in a hippocampal neuron network. Hippocampal neuron network. In other words, what will be, so increase in number of synapses. Further, what this will lead to? connectivity between neurons increases, right. Okay. So, the question which was posed in front of us as cell culturist is how to perform an in vitro neural cell culture assay to test this or validate this fact or proposal. And what is the proposal? That it will increase the number of synapses. So, what all we did? Our approach now comes, now change the color, our approach, I am just now systematically putting it in front of you. So, we needed a hippocampal neuronal network. So, this is all in vitro, so we do not have to worry about the animal studies at this time. So, we reached this far that we have a pyramidal neuron culture system which a random culture system, there is no as such order or anything. So, we developed a culture system using fetal 17-day rat, and this is our hippocampal neuron culture. So, whenever we talk about this increases the number of synapses, so what we are talking about, the synapses actually form between a dendrite and an axon, or even an axon and axons, there are locations which they form synapses. So, let us identify the synapses by, say, let me use red color. Okay. So, these are the zones where synapses will be forming. And this may be getting some input from somewhere, okay, or okay. Okay. Now, you culture the cells, a finite number of cells using on 4 different cover slips. You have to of course increase the replication number. Okay. So, I put 5, there is a reason why I put 5. So, these are 5 cover slips, or in other words you can say 5 different trials. Okay. So, one of, and on each one of them will be say replicating them say 10 times. So, we will be obtaining data from say in this case 50 cover slips, fine, making sense. So, we have 5 different case studies. So, our 3 case studies are already defined, X, Y, Z, and this is your control, and this one, this particular one. This one could be a something which causes, if suppose you know that it causes that specific disease, which causes, or hunch, there is a hunch that it causes AD, some other molecule, Alzheimer's disease. AD stands for Alzheimer's disease. Okay, just let me put that in case you forget, AD. Okay. Now, some molecule, say Q, fine, just a random molecule. This is all hypothetical. Now, on each one of these, so you have for each you have multiplied by 10, multiplied by 10, multiplied by 10, multiplied by 10, 10. So, you are having some 50 cover slips with 5 different possible treatment, okay, out here. So, what you do, you plate equal number of cells on all of them. Equal number of cells on each cover slips. So, you have to ensure couple of things while you are doing that. You have to ensure the source animal are of the same age, they are all your fetal 18, and you are plating it perfectly under the same conditions. You have to grow all of them. Now, you allow the cells and you have to decide when are you going to put your drug, in the beginning or later or whatever. Okay. Now, as a first set of control, what you do, this is control, this is nothing, and you add the drug, and you see whether without any damage in the cells, is it increasing the total number of synapses. How you can validate it? You can validate it by counting the total number of synapses. You can do that by fluorescently labeling these synapses. You can, so whenever we talk about the synapse, it is a zone where, say, this is one neuron, this is another neuron, and they are forming synapses. So, it will be something like this. So, there are fluorescent tags, synaptophysin, synapsin, these are the proteins which are present there, synaptophysin, synapsin, there are several others. Okay. These are the proteins. If these proteins are present there, and if you have antibody against these proteins, so the pink color is showing the antibody, and if this antibody is further labeled with a fluorescent probe. So, for example, I showed the fluorescent probe with this color. This is the fluorescent probe out here. This is the fluorescent probe. So, what you can do essentially, you can count these are called synaptic buttons. Okay. You can count the total number of buttons, you have to do bit of a statistics here. You can count the total number of buttons, and you can say without anything, if we add this x or y or z, what is the total number of synapses in per unit area and whatever. Okay. That I will leave it up to your whichever way you wanted to do that analysis. Followed by, you have this negative control. Here obviously, if there is some damaging element, you add the damaging element Q, and you see the reduction in number of synapses, synaptic buttons. So, what you are quantifying, if I go to the quantifying, what am I quantifying here? So, I am quantifying this in terms of synaptic buttons. So, now you see, try all these 3, then you have this Q, and here you realize you have to increase 3 more treatment. Those 3 more treatments are, so which I did not in the beginning told you, now I am adding them. What you do, you put the Q plus say x, Q plus y, Q plus z. Again, all the applications are 10. So, you realize we are now talking about, you already have 50, now we are talking about 50 plus 30 cover slips, you have 80 cover slips to look into this whole thing, and it is a very random network. Now, how you have to quantify, if you go by the statistics, so you have something like this. You have 8 different treatment with you, right? If I go back, 1, 2, 3, 4, 5, 6, 7, 8. So, you have 8 different treatment. Okay. So, T1, T2, T3, T4, T5, T6, T7, T8. Okay. So, this is your control, this is x, this is y, this is z, this is q, this is q plus x, this is q plus y, this is q plus z. And here you are either you go by percentage or absolute count of synaptic buttons in a random F18 fetal 18 hippocampal neuron network. Okay. So, now you have some percentage. So, you will see certain values coming. Okay. Suppose I assume y performs the best, z is somewhere in between. So, you can have the bar graph like this, okay, something like this. Then say for example, q really brings it down, just hypothetically I am just putting. Say for example, here you see some sort of an improvement, and say y you see a much more improvement, and here you see some improvement or something not. Okay. Now, what you have to do, all these 8 treatments you have to do a comparison. Is it significantly different? Like is T1 significantly different from T2, vice versa, T2 significantly different T3, T3 to T4, likewise send T1 to T4, and you have to do a whole lot of statistical analysis to come to the point that out of all these things, which one stands out or nothing stands out. Based on that, say for example, we say okay, now we have this promising thing with say this one, say for example, then what we will do, this molecule will be taken for the next level of trial. But this has to be repeated several times, and not only that, this has to be done over time window. Say for example, for how many days this acts. Say for example, this culture is this culture of say 5 days, when the assay is being done 10 days, 20 days, 40 days, 2 months, 60 days. Okay. So, at different time point how this whole thing is happening. So, this needs tremendous amount of support in terms of the cell culture and the expertise in it. But then when we say this, let us see what are the problems you are going to face in this. There are certain problems which are going to emerge, and that is what I am going to highlight now. What are those interesting problems what you are going to face? The first problem, you try to realize, this is the word I have been using very repeatedly, is it is a random culture, right. Now, your hippocampus, if you look at the tissue, if you remember when I showed you the tissue. So, you have CA1, CA2, CA3, CA4, you have the dentate gyrus sitting here, DG, CA1, CA2, CA3, CA4, all these pathways which are rolling. This is a very systematic pathway. Okay. Something like this. It is a very unique systematic pathway. So, when we talk about a random scenario, what I showed you in the previous slide, if you look at it, it is a very random network. So, this is not the true representation, this is not a closer representation to, not, mark my word, not a closer representation of a real life hippocampal network. Yes, it is part of it, but not close to the real life. Okay, random culture, not a exact representation. Point 1. So, challenge, could we mimic, and form solutions. So, let me class solutions, possible solutions, of course not solutions, it should be possible solutions. So, this is the, we are talking about the drawbacks here. Drawbacks. What are the key aspects? Okay. Now, solution. Could we mimic and form a patterned network? Point 1. Now, that will take us to the domain of substrate engineering. Second, what is the second drawback if you look at it? It's a random culture first. Second inherent drawback with the system is, in a random culture, quantification becomes very difficult. Quantification is challenging and ambiguous. That can only be resolved if we have a pattern network. So, they are linked. The second major drawback is, what we have used is a 2D culture. It is a two-dimensional culture, but this whole structure is it has a z axis, right? It has a z axis, it has a x axis, it has a y axis. Fair enough? So, where is the z axis? Now, could we make a 3D culture? And the challenge will be, could we make a 3D pattern culture? That is where the future is. You are almost trying to mimic that organ in a dish, and that will take us to lab on a chip concept. Third point. Now, 3D and 3D pattern. So, we are taking one step. Now, the most challenging part of the game is something else. Now, what you are using is an F18 tissue, but here I will close in. Alzheimer's does not happen to a fetus, right? It happens to an adult. Now, you wanted to represent a disease which causes to an adult by using a culture which is of fetus. That's something really ponder upon. Are we representing the right age by picking up that model? So, what are our options? Here is our option. You have to do this in adult. Now, adult hippocampal neuron culture. And this adult hippocampal neuron culture further, if it could be on 3 dimension as well as a pattern. So, all the 3 together, that will be the bingo if we could really create a model which will be almost, I am not saying the closest, but yeah, definitely will be closer than what we are doing today. So, you realize we took up a simple case study, but through that case study we are traveling into a different domain, how we get around this problem. So, I will close in here. In the next class, we will talk about this. Thank you.